Modern computational security and cryptanalysis trace their origins to Alan Turing's work breaking the Enigma code during the Second World War. The German Enigma machine represented a closed, trusted physical system. It was an impenetrable black box used to secure all communications, functioning on the premise that physical possession of the hardware guaranteed security. Cracking that closed hardware system from the outside required an immense operational scale at Bletchley Park, involving hundreds of mathematicians, logicians, and early computing devices. Classical cybersecurity was born from this specific struggle, the effort to break into physical hardware owned and guarded by someone else. Modern computing has entirely inverted that dynamic. Today, instead of trying to break into closed systems, we willingly push our most sensitive data right into them. We see this with software as a service, or SaaS. When users access web-based email, they are outsourcing the hosting and operation of that application to a third-party provider. Infrastructure as a service, or IaaS, pushes this abstraction deeper by granting users raw access to virtual machines instead of just software. A virtual machine is a software-based emulation of a physical computer that runs an operating system and applications. Whether utilizing SaaS or IaaS, the operating premise is the same. The user surrenders control of the physical hardware to a remote provider. This creates the core dilemma of the cloud. The environment acts as a black box, where clients have zero visibility into or control over what physically happens to their data inside the provider's data center. This dilemma introduces a massive hidden insider threat. Even if the corporate cloud provider operates honestly, malicious system administrators within that company have direct privileged access to the underlying hardware and virtual machines. Any unencrypted data sitting in either a public or private cloud is fully readable by the provider's staff. Moving to the cloud does not eliminate hardware risks. It simply transfers those risks to an unseen, unmanageable third party, breaking the traditional chain of trust. This slide outlines the four-tier architecture of cloud security: facility, network level, operating system and application level, and data level security. Facility security protects the physical perimeter by locking server racks and securing the building, while network security operates digitally to prevent unauthorized routing and network attacks. At the data level, traditional issues regarding confidentiality and integrity remain a major threat to cloud environments. This list shows specific offline password cracking methodologies used against these data layers, including brute force, hybrid, dictionary attacks, and rainbow tables. A rainbow table is a pre-computed dictionary of plain text passwords and their corresponding hash values used to rapidly crack encrypted password files. While these traditional vulnerabilities persist, they are eclipsed by the unique structural threats introduced by the technology that actually runs the cloud: virtualization. Virtualization is the process of creating a software-based representation of physical resources, like servers or storage. Virtualization acts as the core engine of cloud computing, allowing a single physical server to be partitioned into multiple independent environments. This diagram illustrates the virtual machine manager, which handles the creation, editing, starting, and stopping of isolated virtual machines. The manager centralizes oversight, allowing administrators to view live performance and resource utilization statistics across all running hosts and guest consoles simultaneously. Because the virtual machine manager and the hypervisor centralize control over all virtualized hardware, they inadvertently consolidate the entire attack surface into a single logical layer. A hypervisor is a piece of software that creates and runs virtual machines by isolating them from the underlying physical hardware. This slide highlights vulnerabilities specific to multi-tenancy. Multi-tenancy is an architecture where a single instance of a software application or physical server serves multiple distinct customers. Because of this, a client never knows whose virtual machines are sharing the same physical server with them. This diagram details an inter-VM attack. Here, an attacker intentionally targets neighboring virtual machines hosted on the exact same hypervisor. The attacker exploits shared physical resources, such as a shared folder, to maliciously alter the disk image of an adjacent virtual machine. Attackers also utilize side-channel attacks, where they monitor the physical behavior of the shared hardware, like memory patterns or CPU cache timing, to infer the data processed by a neighbor. In a multi-tenant environment, physical proximity equates to shared vulnerability. An isolated virtual machine is strictly as secure as the hypervisor isolating it. To optimize resources and balance computing loads, cloud providers constantly execute live migrations, moving running virtual machines between different physical servers on the fly. This schematic illustrates the architecture of a live migration, showing a virtual machine's Unix kernel detaching from its original host hypervisor on the left side of the security zone boundary. Here, the virtual machine's data crosses that boundary, utilizing shared storage to reattach to a new destination on the right. This exposes a precise window of vulnerability. When the virtual machine is actively in transit across the network, its integrity can be intercepted. The features that make the cloud highly flexible, like resource pooling and live migration, actively create dynamic security gaps that static, bare-metal physical servers never faced. There is a dual pathway for virtualization compromise. An attacker can breach the hypervisor directly to attack the virtual machines, or they can breach a single virtual machine to attack the underlying hypervisor. In an escape attack scenario, the attacker compromises a guest virtual machine and uses it to execute malicious code against the hypervisor itself. The outcome of this is catastrophic. Upon gaining root access to the hypervisor, the attacker owns every virtual machine on that physical host, entirely violating multi-tenant confidentiality. Root access is the highest level of administrative privilege, allowing unrestricted control over a system. Relying solely on the cloud provider's virtualization boundary to protect your data represents a dangerous single point of failure. The cloud functions as an impenetrable black box. Any unencrypted data entering this environment is immediately exposed to malicious internal administrators and lateral inter-VM threats. The absolute mitigation strategy is robust client-side encryption executed before data leaves the user's local device. True cloud security requires accepting the environment as inherently compromised. Your data protection must be completely independent of the infrastructure hosting it.